I like to say that 1847 is the year of energy. That was the year in which James Prescott Joule shared with the world his results, linking the amount of thermal energy produced in a situation to the amount of mechanical energy that was lost. It was also the year, though, that another paper was published that linked the amount of work done by a force to something to the amount of kinetic energy that that object would acquire, at least in the absence of other forces. And so that really demonstrated to the world that there is a new concept that connects energy to forces and establishes it with a good mathematical foundation. So that's what we're looking at here, the topic of work. And this first line on the key concepts page is maybe shouldn't be allowed in physics 2A. It's a calculus based thing. So maybe we should start actually at the bottom here, but I'm putting it here just to so we all recognize this is like the fundamental definition of work. But work at a very conceptual level is just force times displacement. In other words, if you apply a force to an object, so let's say here's an object, okay? If you apply a force to that object, so I'm going to apply this force F to that object, and that object displaces some distance d as a result of that, then I did an amount of work to that object that equals its force times its displacement, okay? And that's the simplest concept of work right there. So I've labeled that as maybe the simple formula is multiply force times displacement. And if you have a situation like this, you can just do that. And maybe I should relabel that here as simplest, right? Because it turns out the next one here is still relatively simple. It's just not simplest, maybe. What happens, like let's say, what if instead of applying a force in the direction of the displacement, what if I had an object, and maybe because it was on the ground or something like that, and I applied a force at some other angle, but let's say it's still displaced horizontally. That's what this second formula is for. Situations like this. The force is constant, though, throughout the process, and the displacement is a relatively simple straight line. So that's pretty much true for both of these, but in the simplest case, again, they're both in the same direction. In the slightly less simple but still simple case, we're going to need to figure out an angle. So if I gave you a problem like this, I'd have to give you some information that lets you figure out what the angle between the force and the displacement is. Here I've put as the last formula on the whiteboard, the one I put first over here, so I'm kind of the opposite direction here. I was going from hardest to simplest. Right here I'm going from simplest to hardest. This again is the definition and accounts for situations like, let's say I had an object where maybe the force is not constant, maybe the displacement is not in a straight line, or maybe both of those things. That's pretty much when you'd have to use this more fundamental definition of work. But really what this is like just the sum of forces times displacements over like breaking up that motion into little tiny intervals. However, this is going to be a not our class, so it's not physics 2A. We're not going to be doing anything with this, so in that sense we may as well cross it out of our minds for the purpose of this class. We're just going to be doing the simplest and the simple type of situations for calculating work.